Okay, so here we go. Section 7.5, number, what did I just say, 41. So big in this. Okay, so it says a single force acts on a 3 kilogram particle. So our mass is 3 kilograms. It tells us, it gives us an equation for the position at a given time. It says the position is 3.0 t minus 4.0 t squared plus 1.0 t cubed. With x in meters and t in seconds, find the work done from t equals 4, or t equals 0 to t equals 5. So work equals what from t equals 0 to 4. Okay. Thoughts? Anybody figure this out? Sure, they got. Okay, you're totally in the right neighborhood. So the only problem with that, so you're saying take a derivative to find the velocity, take a derivative to find the acceleration, right? And then do mass times acceleration to get force. Okay, but that'll work, but it makes it super complicated because what happens is if you take a derivative of this, your first derivative is going to bring this down to t squared. So your velocity is going to be proportional to t squared. Your second derivative is going to bring this down to t. So your acceleration is proportional to t. In other words, your acceleration is not constant, which means your force is not constant. Does that make sense? So to go that route, what you then have to do is you have to integrate your force with respect to x. But the problem is our bounds aren't x bounds, they're time bounds. Do you know what I mean? Like when you do work equals the integral of force, it's dx, not dt. Okay? So you'd have to figure out, oh, I guess you could do that. You could just plug it in. Oh, that actually will work. That will work. But you'd have to plug in your time here to find your position at each of those moments. All right, so does that make sense? All right, that said, I think there's a slightly easier way. What do you got?
I found the velocity equation. I found the velocity at 4 and 0, and then
yeah, so I think the more direct way of doing it is to do this. We know that our net work is just the change in kinetic energy, right? And kinetic energy is, well, 1/2 mv squared, right? So I can find the velocity at 0 seconds and at 4 seconds, then find your two kinetic energies and subtract and you're done. Make sense? That's one less derivative and no integrals. Follow? All right, so let's do that real quick and see how that works for us. Okay, so if this is our x, then v is dx dt, so we got to take a derivative of this guy, so you're going to get 3 minus 8t plus 3t squared, right? Follow? So v at 0 seconds is going to be, what, 3? And after 4 seconds, we're going to get, I don't know, some number, let's see. 3 minus 32 plus 16 times 3 is 48. Did I do that math right? Oops. So 16 and 3 is 19. Good? All right, so now I know those two velocities. I know my mass, I know my velocity, so I can find this kinetic energy, find this kinetic energy, and then just subtract and you're done. Follow? Is anybody going to be stewing if I stop there? Good? All right, right on. Okay, so somebody wrote 7.5 all. I have a suspicion that I may know who it is, but I'm not 100% positive, so I will not accuse that person. I just said I'm not going to accuse the person. Oh, was it? Oh, all right. Well, I'm glad my accusation would have been false then. Oh, okay. So I'm extra glad I didn't say anything. All right. Yeah, why would Marcus write anything up that? All right. That wasn't meant to me, Marcus. I meant that to be totally inaccurate. I'm sorry. All right. So, are there specific ones that Alex or anybody wants me to do from 7 to 5? Which one? 57. This, incidentally, you guys, this is, I feel like a pretty reasonable question. Right? Because it was 2 steps, right? Derivative and find your kinetic energies. I guess that's more than 2 steps. So, okay. What did you say, 57? Oh, right. I'm really glad you chose this one, actually. Because it hits an idea that I think I have not done a great job stressing. And as I was writing the test, I was conscious of this, that I felt like I hadn't stressed this concept. And there is a point where it comes up, so this is important. All right? So it says a 230 kilogram crate hangs from the end of a rope of length 12 meters. You push horizontally on the crate with a varying force F. So the force is not constant. To move it, the distance d equals 4 meters. So you can't just do force times 4, right? Because your force is not constant. Okay? If you wanted to go that route, you'd have to take an integral, which gets really ugly. All right? But, so here's the idea. So here's your crate. It's 230 kilograms. Why they chose such a big number, I don't know. Here is the force that you're applying. You cause it to swing up to this point here. We know this this radius, this length is 12 meters. Same thing over here, 12 meters. The crate begins at rest. So the velocity here is 0, the velocity here is 0. All right? Now, question A says, what's the magnitude of the force F when the crate is in this position? So in other words, when it's at this point, you're keeping it at rest, correct? Okay. So that one is basically just some trig. So at this instant, there are 3 forces acting on the block, right? Name them for me. What do we got? Force of gravity. I guess, yeah, 4 forces. There's force of tension in the y direction, force of tension in the x direction. Oops. Force of tension in the x direction, and then the applied force, right? What has to be true about all those forces? They all have to cancel, right? So let's see. You got to do a little bit of, let me grab my answer key here, just because it'll have numbers in it. I don't need to recalculate stuff. But so the idea is I know this distance, so I can find this angle, right? Okay. And since I know FG, I know FY, and then I can use trig to find my x component, right? And then find F, right? Does that make sense? You guys, I'm happy to run through it if you guys want me to.
Can you run through?
Yeah. Okay. Thank you for being honest, because that was a mouthful that I just said that. What do we got? Number 57, chapter 7. All right. Okay. So this triangle here has sides. This side here is 4 meters. This side here is 12 meters, right? So that gives me enough that I can find this angle up here, right? Follow? Or I guess really I should probably find this angle. All right, so let's call that angle theta. If you figure it out, it turns out to be 70.529. Let's just call it 70.5 degrees. Good? All right, now, I know the mass of the box, so I know my force of gravity here is going to be just 230 times 9.8, which gives you, somewhere I have that written down. $22.54, is that right? I did not do a good job of labeling. Oh, there it is, yeah. So this is $22.54. Everybody good with that? Just by doing 230 times 9.8. So since the box isn't moving, that means that my y component also has to be 2254. Good. And so now I can find my x component by doing some trig, right? Because my force triangle now looks like this. Oops. My y component is 2254. And this angle here is 70.5 degrees, right? So I can do a little trig and find this x component, right? So if you do that, that x component turns out to be 796.9. Did I say that right? 796.9. And therefore, the applied force has to be that same value, right? Good? Everybody good? Okay, so that's the deal then. All right. Part B, find the total work done on it. Smiley face for the answer.
0.
Why is it 0?
That's 0.
Because there's a smiley face. Good. Very good. Although not always, but often, yeah. Yeah, our starting kinetic energy is 0, our ending kinetic energy is 0. Therefore, our change in kinetic energy is 0. Work is 0. Good? All right. Part C says find the work done by the force of gravity on the crate. So let me kind of clear up the board a little bit here. Am I going to be able to? No. Out of my way. There we go. Okay. Aha. Take that, smart board. Yep. Okay, so we got to find, for part C, we got to find the work done by gravity, right? So work done by gravity, you guys, is just your force of gravity times your vertical displacement, right? So I can use this little triangle here to find my vertical displacement, can't I?
Is it always just vertical displacement?
Yes, because gravity points down, and we're interested in the component of displacement, which is parallel to that, or anti-parallel in this case.
Okay, so if you found the total displacement of the box took, and then found the angle between that and gravity, would you get the same thing as?
Yes. Yeah. Yeah, totally. Okay, so this is going to be force of gravity times our vertical displacement, right? So my force of gravity, we already figured that out. That's 2254 newtons times, shoot. So I already shrunk this drawing here. So it turns out if you find this other leg of the triangle here, we got 12 and 4. So the third side using the Pythagorean theorem gives you 11.3 meters. So our vertical displacement then must be what? 0.7, right? Does that make sense? Everybody good? It's actually 0.6 something. 686, I guess. If you actually do the math. All right, so anyway, so multiply that out. That gives you your work done by gravity with one small mistake. It's negative. Why is it negative? What did I miss here? The displacement is up, the force of gravity is down, so you need to indicate the difference in direction there, right? Clear? Any problems? Okay. D, find the work done by the pull on the crate from the rope. So this is tricky. This one's really tricky. How do I want to explain this most directly? The problem is that the direction of that force is always changing, right? The tension force is always changing, right? Well, not only is the direction changing, but the magnitude of it is always changing, right? Okay? So that makes things pretty complicated, right? So technically what we'd have to do is we'd have to write an expression for the x component of the force, and then integrate that with respect to dx, and find the y component and integrate that with respect, to dy, and go from there. But there's a way easier way to do it. Okay? At any given instant, so here's the crate, right? Isn't the path that it's following circular? So at any given instant, my tension force is this way. And my velocity is perpendicular to it, right? Tangent to the circle, perpendicular to the radius, to the force, right? All right? So what that actually means, you guys, is this. Remember, power, and this is a total cheat, but it works. The power being generated at any given instant is force dot velocity. Hear me out here, and then when we're done with this, I'm going to tell you something super important, and it's always true. So right now, some of you are like, I never would have thought to do that. After I tell you this one thing, you won't need to think to do it anymore because you'll know it. Okay? So, all right. So the power is force dot velocity, right? What's the dot product of two things that are perpendicular? 0, right? So my power is always 0, right? Well, check it out. Power is work divided by time. Therefore, work is power times time. But my power is always 0. So the work is 0. All right? If your force is perpendicular to your direction of motion, it's not doing work. Okay? So we knew that if the force was perpendicular to the displacement, we weren't doing work, right? But here it's confusing because your direction of motion and your direction of force are always changing. But because they're always perpendicular, they're not doing work. Follow? All right, if it helps any, here's a simple analogy of this. So if you have a box sliding down a ramp, you guys all know the normal force doesn't do work, right? Because the normal force is perpendicular to your displacement, right? Well, on a roller coaster, that's an inclined plane with a changing slope, right? But the idea is, again, at any given instant, your normal force is going to be perpendicular to your direction of motion. So even though the direction of your normal force is always changing, it's always perpendicular to the direction of motion, and therefore it doesn't do work. Does that make sense?
Yeah.
Right? So normal force will never do work. Well, I shouldn't say that. If the object is sliding or rolling on the surface, the normal force doesn't do work. Right? And same thing with centripetal force will never do work. Right? Good? Questions on that? That's a big idea. Yeah, go ahead.
The force is perpendicular to the velocity.
Correct. Wait, say it again, sorry.
If the force is perpendicular to instantaneous velocity, the force is
Correct. Oh, well, that gets sloppy. Because you can't talk about work at an instant, right? Because work, by definition, is changed.
Okay.
But if your force is always perpendicular to your velocity,
Okay.
then as long as that's true, the work done during any time interval there will be 0. Follow, you guys? All right, cool. Okay, so finally then, question E says find the work done by your force. Well, look, you guys, there are only 3 forces on this thing, right? Gravity, tension, and U. We know that our net work is 0, right? So let's see, work net is the work done by gravity plus the work done by tension plus the work done by U. We know all of these except one. Our net work is 0 because we started at rest and ended at rest. The work done by gravity is negative 1550. The work done by the tension is 0. The work done by U is something. It's got to be 1550. Follow?
Yeah.
Work kinetic energy theorem is huge. That's all this is again, right? Good. All right. All right, and then shoot, what did I Why is the work of your force not equal to the product of the horizontal displacement and the answer to A? Oh, just because your force is always changing. And the direction is changing. Yeah, your force vector is always changing. So. Great. Are we good with this? Yeah. All right, so we should move on to 7.6 because we've not spent much time with power at all. So let's do that real fast. We got about 20 minutes here. So what is that? 43, 44, 47, 48, 49. All right, let's see what we get through. While I'm circling those, you guys take a look and see which ones you want to go over. We'll do a quick vote again. Oh, it's pretty much all of them. I will say there's not a huge emphasis on power on the test. Like there might be, I think at most 2 problems about it, and they're, I think, pretty basic. Yeah. Ooh. I don't know off the top of my head. I'm not as familiar with that equation sheet as I should be. But I mean, to my mind, there's only the equations that you need to know are F equals kx for a spring and U equals 1/2 kx squared for potential energy of a spring, right? Or work done by a spring, I guess I should say. Sorry. W equals 1/2 kx squared for a spring. Kinetic energy is 1/2 mv squared. And then work kinetic energy theorem, and I think you're probably good.
You need to have a calculator. So.
Oh, right. Yes. All right. Are we good? I will 100% look the other way on that because you can do that in the AP test. So, all right. So, preferences between those up there. We got basically 43 through 49. So, which ones are jumping out at you guys? 48. Anything else? All right. Let's start there then. 48. A 0.3 kilogram ladle. Who writes these problems? It's terrible. All right. Here we go. 48. Sorry, Internet public, if you're watching this video hearing me knock this book. All right, so we know that the mass of our object is 0.30 kilograms. It's sliding on a horizontal frictionless surface. So there's my ladle. Mass is 0.03 kilograms. I know. It's attached to one end of a horizontal spring whose other end is fixed. That was funny. Ladles to springs, dude. What else? All right. All right. The ladle has a kinetic energy of 10 joules as it passes through the equilibrium point. So x equals 0, k equals 10 joules. Shh. All right. It says, at what rate is the spring doing work on the ladle as the ladle passes through its equilibrium position? All right, so what is that called, the rate at which we do work? Power, right? So that question is really asking you for the power. Now, we learned two ways of finding power, right? You can find the average power by doing work divided by time, but that's not what this is asking for. This is asking at what rate is it doing work at that instant. So it's asking for the instantaneous power. All right? And the only way we've learned to calculate instantaneous power really at this point is to do force dot velocity. Okay? Now, at this instant, we know it's got a kinetic energy of 10 joules, so it's got some velocity, which we could certainly calculate because we know the mass, right? But why is the force 0? Yeah, the force of the spring, you guys, is k times x. Well, if x is 0, your force is x. So you're going to have 0 force times whatever your velocity is, you're going to get 0. Does that make sense? The idea is the spring isn't exerting a force at that point, so it's not either making the box speed up or slow down at that point, right? Okay, so that's part A. Part B, at what rate is the spring doing work on the ladle when the spring is compressed 0.1 meters and the ladle is moving away from the equilibrium position? Okay, so let me do this. Oh, that's not what I want to do. Okay, so at some later moment, the box is going to be over here at x equals 0.10 meters. I won't draw the spring in because that'll clutter the drawing. But and so the question is, what's the power at that instant? Okay. So what two things do I need to know? The force and the velocity, right? Okay. So what forces are acting on the box that are going to do work? Just the spring, right? So let's figure out how much work the spring did between here and here. Okay? So remember, the work done by a spring is 1/2 kxi squared minus 1/2 kxf squared. That is an equation. You were asking about equations, Marcus. This I'm not sure, but I'm guessing this is not on that sheet, so you should know that or put it in your calculator. All right? So, good? Yeah. All right, so my initial position is 0. So I'm going to get 0 minus 1/2 of 0.1, nope, sorry, got my K. K is 500 newtons per meter. Newtons per meter times 0.1 meters, don't forget to square it. So you're going to get half of 5, which is what, 2.5? Negative 2.5 joules. So what's that telling me, you guys? What does that mean? The work done by the spring is negative 2.5 joules. What's that telling me? Say that again. Very good. That's the change in kinetic energy. It's telling me that we lost 2.5 joules of kinetic energy. How much did we start with? 10. So that means that my kinetic energy at this point is 10 minus the 2.5 we lost, so it's 7.5 joules at that moment. Good? Yep, I cheated, so it's this. Change in kinetic energy is, by definition, final kinetic energy minus starting kinetic energy, right? Like, because that's what change in something means. It means final minus initial. So I know my change is negative 2.5. Let's figure out how much we ended up with after starting at 10.
Okay.
Follow?
Yeah.
So add 10 to both sides and you get 7.5. Yeah.
For the exit point 1, it says compressed, but it doesn't matter which way you go.
Oh, did it say compressed?
Yeah.
Oh, okay. Yeah, it doesn't matter. It doesn't affect the problem at all. Because either way, remember, this was what we were talking about yesterday with that drawing with the springs on both sides. That no matter which way you distort the spring, whether you're compressing it or stretching it, the spring is still going to apply a restoring force in the opposite direction of motion. Okay? You guys good? You sure? Okay. All right. So, So what were we trying to find again? Power, right? So power is force dot velocity. Well, check it out. At this moment, I know the kinetic energy, so I can find the velocity. And I know the displacement, so I can do F equals kx and find the force. Good? My velocity is this way. My force is that way. Right? And so the power is going to be negative, whatever that gives you. Make sense? Would you like me to finish it? I'm more than happy to if anybody wants me to. I always feel guilty when I don't finish these. I need to get over it. Are we good? We're good? Okay. All right. So that's the deal on that one. I feel like I haven't told you anything sort of enlightening about how I knew to do that. I guess here's what tipped me off. We were looking for power, and the only way we've learned to find power is force times velocity. Sorry? Oh, right, or using the integral, but it gets ugly. So I haven't seen any problems in the book, at least, where we've had to do that.
So can you assure us, without a shadow of a doubt, that they're not going to be?
You cannot. There's one very simple integral.
Okay.
Okay. And it is easy, and it's good. It's fine. Yeah. All right. All right. So anyway, I knew we needed the velocity, so that led me in the direction of thinking about kinetic energy. So we're kinetic energy there. Good. All right. What else, you guys? We got about 10 minutes. We can probably get through 2 more of these. References?
45.
45? Any objections? I legitimately don't know if there are any. Let me do 45 and then I'll do that. The integral one, shoot. Most of the integral problems we've done have been this. And we did a really complicated one of those yesterday right at the end of the hour, right? Oh, yeah. All right. Finally figured out the little pink thing here. So, okay, what am I doing? I'm doing 45. All right, 100 kilogram watt. So mass, 45 kilograms. No, wrong. That's the problem number. Mass, 100 kilograms. Is pulled at a constant speed. Ooh. V equals 5 meters a second. Constant. That means automatically that my network and my change in kinetic energy are 0. I hope that proves to be helpful. All right, so it's pulled across a horizontal floor by an applied force 127 newtons directed at 37 degrees above the horizontal. So our force is, what did I just say, 122 newtons at 37 degrees above the horizontal, right? And it says, at what rate, what is the rate at which the force does work on the block? So again, what are we looking for when I say that? At what rate is it doing work? Power. Are we looking for average or instantaneous? Although actually in this one it doesn't, I don't think it matters even. Yeah, it doesn't matter because your force is constant. Yeah, I think, yeah, it's going to be the same thing. So we'll see why in a second. Okay, all right, so I'm trying to figure out how to explain why we can find instantaneous instead of average, or that it doesn't matter. So tell you what, let me find instantaneous and then talk about why the average is the same. Fair? All right, so check it out. So instantaneous power is force dot velocity, right? That's the same as FV cosine theta. Right? Well, oh, I know my force. That's 122 newtons. Is that number changing?
No.
Nope, it just says a force of 122 newtons. Doesn't say anything about it changing. We know the velocity is 5 meters a second. And the angle's 37 degrees. So just multiply it out and it gives you 490. All right, so check it out. If I'm driving at a constant velocity of 60 miles an hour, isn't my average going to also be 60 miles an hour? Same thing here. If my instantaneous power is always 490 watts, then as long as it's not changing, my average is going to be 492. 490 also. Good?
What would make that?
If either the block sped up, or the force changed, or something. Good? But here, everything's constant. Well, I guess except the energy. Oh, wait, no, the energy's not changing either. So everything is constant. The position's not constant. There you go. So it's changing. Ah, very good question. He said, how can there be a force while the velocity is constant? You got an idea, Alex? Yeah, there could be some other opposing force canceling out that x component. All we're doing is we're finding the power generated by this one force, not the net power. So good follow-up question. What's the net power in this problem? 0, right? Because whatever energy is being added in by this force is being taken away by friction or some resisting force. Follow? All right, one other one. We got a couple minutes. We can do one more. Francis, you put those on the board. What do you got? Oh, 47 or 49? Yeah. Thank you for speaking up. All right, here we go. 49. What do we got? Let's see. A fully loaded, slow-moving freight elevator has a cab with a total mass of 1,200 kilograms. It's required to travel upward 54 meters. So our change in vertical position is going to be 54 meters positive in a time of 3 minutes. Why did I say it like that? That's 180 seconds. Ugh, stupid units. All right, it says the elevator's counterweight has a mass of only 95 kilograms, so the elevator motor must help. So, sorry? No, it says 950. Right? So what does that mean? What is it talking about, counterweight? I don't know a ton about elevators. What do you think that means? Yeah, it's one of these. There's a pulley in there somehow, right? So you've got your elevator. So this is, what did I say, 1,200 kilograms. Counterweight, 950 kilograms. All right? So there's our counterweight, right? Okay. So the elevator motor must help. What average power is required of the force the motor exerts on the cab via the cable? All right, so here's the deal. It's got to start and end at rest, right? Okay. So there are going to be 3 forces doing work on this thing. Okay, right? So it's going to start and end at rest. My change in kinetic energy, my net work is going to be 0, right? And my net work is the work done by gravity plus the work done by the counterweight plus the work done by the motor, right? Follow? All right, so let's see. I can figure this out, right? Let's see. My work done by gravity. That's going to be the force of gravity, so 1,200 kilograms times negative 9.8. I'm doing this I'm combining some steps here to save time because we're a little tight on the clock there. So that's the work done by gravity, right? Right? Just force of gravity times the height. Good. Notice it's working against the motion, so I put the negative in on the 9.8. In some fashion, the work done by gravity is negative because it's going up, gravity pulls down, right? Okay. What's the counterweight doing? Opposite. It's helping, right? It's pulling up. Presumably with a force equal to its weight. It's probably sort of an oversimplification, but it works in this problem because that's the maximum that it could exert. So I'm going to do this. I'm going to do the force this can exert is up to 950 times positive 9.8, right? Because it's pulling upward, times 54 meters because of the pulley.
Wait, so the elevator's going down?
No, the elevator's going up, the counterweight's going down. So since the counterweight is going down, it's pulling the elevator up, right? It's just...
So why is the elevator negative?
So it's
Oh, that's gravity.
This is gravity on the elevator. So gravity's pulling down while the elevator goes up. So gravity's working against the elevator's motion.
Okay.
But the counterweight is working with the elevator's motion. Follow?
Yep.
All right. Plus the work done by the motor, right? Good? So solve it, and that gives you some number. And then divide by 180 seconds. Does that make sense? Questions on it, you guys? Okay. Now this is it's not sloppy, but I just want you guys to understand that technically speaking, real quick, we have to do a little extra force to accelerate it, but a little less force to stop it at the top as those differences balance out. Good? All right. I'm around after school today for about 45 minutes, half an hour, and I'm here early in the morning.
Okay, so a watt.
Yeah.
Yep.
What is the
Newton's times meters. Right? Work is force times distance, so it's Newton's times meters.
okay?
It's a Newton meter, yeah. Yeah, sure. Yeah. Do you have a first hour that you can get to?
Yeah.
Okay. So I was going to say, if you do, make sure you're here by 7-ish. If you're not worried about getting first hour, then...
Yeah, Jared, or like,
Just so you guys know, I've got a class starting my first hour. They're taking a little quiz. So I can't, and my point is I can't come on in total silence.
that's,
Hey, Jared, did you get your question answered over here? Whenever you and, you're good? Francis, are you good? All right, I'm not going to have, between tonight and tomorrow, I'm not going to have time to put those last couple answers on the board.
I'll try to figure them out tonight with what you did so far, and if I have more problems.
Okay, and the power stuff on the test is very minimal. So, like, no
That's
force.
my hardest one, so.
Okay, right, yeah. So no, it's force dot velocity, and know the 2 ways of taking dot products, right? That equals n theta or you know, multiplying your I components, multiplying your J components, you know what I mean? And then average is what we just did, find the work done, divided by the time. You know that you're mistake.
Thanks.
You're welcome, I'll see you later.
Is it possible I can take the quiz today for the test?
Well, it depends on how long you think you're gonna take. You feel like you know the material pretty well? It's 1 page from that.
Yeah.
It's the target check and what we did today.
Okay, then maybe 15, 20 minutes.
Okay, yeah, I mean, you have more than that, but I don't have an hour.
Okay, yeah, I won't see an hour.
Okay. Yeah, I'm sorry, I felt terrible giving you guys a test on the last day.
Oh, that's fine.
But I thought it was better than having you guys relearn everything after break.
Yeah. No, I
Because
understand.
these will be on the final, but very, very simple versions of the problem.
Okay.
Here you go, holler at me if you need anything
I
clarified.
have one question before I start.
Yeah.
If it's like between a car, like we did one example where it's like the car and then like the street, this friction or the road is friction. How would I like write that in a sentence?
So your action would be the force of the street or the road or the ground.
Okay, so I can't say force of friction.
No, this is not an object.
Okay.
So you gotta identify the object so the friction there would be between the car and some other object.
Okay.
The road or whatever.
Okay.
Make sense?
Yeah, I got it. All right, thank you.
Yep. Ugh.